let's do in this video a example of gravitational acceleration when it's a two-dimensional problem. So in this case, we have a kicker in football, and he's trying to kick a field goal. And just to make our life kind of easy, I'm going to assume that he has to kick the ball 50 yards from the point where he kicks it to the point where it hits the ground on the other side. We're not going to worry about whether it makes it over the upright, just to keep our lives a little bit simple in this first example. So it needs to travel 50 yards through the air before it hits the ground. What initial velocity should he kick the ball at? And we know he wants to kick it at a 30-degree angle because that's determined by, let's say, the height of the special teams that are charging towards him. He needs to kick it over their head, so he's got to kick it at a 30-degree angle. Okay, so let's do it. First thing you need to do is identify that because gravity is the only force acting on the football, this is a problem where the acceleration is gravitational acceleration, and you can apply kinematic equations to this situation. Since this is a two-dimensional problem, you're going to have to apply the two-dimensional two-column approach. But first, let's sketch the problem. Before we even get started worrying about all those details, let's make sure we have a clear picture of the problem. So the football starts out over here, and it gets launched at some initial velocity here. So let's call the initial speed will be VO, and we know that it's 30 degrees above the horizontal. The football will take a path through the air, which is a parabola. Constant acceleration causes a parabolic path through the air. And then finally, over here somewhere, the ball will end up here. And don't forget here, the final velocity is not 0 because the ball hasn't actually hit the ground yet. Because as soon as it touches the ground, kinematic equations cease to apply. So it does, in fact, have a non-zero final velocity, which will be in some direction like that. So that arrow is the final, that arrow is the final velocity vector. And the other thing I know here is that I want the ball to travel 50 yards from here to here, which I've given you the unit conversion here just so I don't have to do it in the video. 45.72 meters. A meter is roughly a yard. Okay, so there's my setup. Now I can actually get started. So I need to start listing knowns, x direction knowns, as well as y direction knowns. Okay, so first of all, the whole point of this problem is it's a gravitational acceleration, which means x acceleration is 0, y acceleration is negative 9.8 meters per square second. Okay, let's reread the question now and say, what else do we know? We know that his initial velocity is 30 degrees above the ground. We don't know its magnitude though. So the initial velocity is actually like half known and half unknown. Because remember, a vector has two properties, magnitude and direction. The magnitude is unknown, the direction is known. So initial velocity is kind of half and half in this problem. So let me add it to my table. I'm not going to worry at this moment about the pedantics of whether I want to call it a known or an unknown. But in any case, let's include it, because I clearly am going to need to do something with it. So it's going to be unknown VO cosine 30. And the y component here is going to be unknown, the same unknown VO sine of 30. All right. And the other thing I know is that it's going to travel 45.72 meters before it hits the ground. So delta x is 45.72 meters. There's one other thing I know, which might be a little bit tricky. I'm just pausing for a second here to see if you can figure it out for yourself. There's something else that's kind of implicitly known here. We know that the ball is going to travel 50 yards before it hits the ground. but we also know it's going to end up hitting the ground. And because it's launched from the ground and it ends up hitting the ground, that means the delta y equals 0. So don't forget about that one. Zeros still count as known information. Don't forget about zeros. Now, in this case here, it's a little bit squirrely to try to figure out if I have enough information to solve yet, because I have 2 knowns in each column, and then I have like 2.5 knowns in each column. So I don't quite have enough information to solve. I have like 2 equations with sort of 1.5 unknowns each or something. But here's the trick you use when you get yourself into this situation. This comes up actually a lot in 2-dimensional kinematic equation problems, especially ones involving gravity. I am just going to add to my list, I'm going to add time as an unknown. There's nothing in the question about time being an unknown, but I'm going to put it in here specifically because if I include time in my equations, it will allow me to build a system of equations, because time is the only variable that appears in both x direction and y direction. So I can kind of use time as a way to link my equations together so that I can solve one equation and plug into the other equation and create a true system of equations. So that turns out to be something that is frequently helpful to do if you get yourself into that situation where you kind of sort of have enough information to finish, but sort of not, and you can't quite build up your equations. So if you are willing to accept for the moment that that's going to work, I now have 4 entries in my x column and 4 entries in my y column, which 4 entries is the number I need to build an equation. It's the same 4 entries in each column, so it's going to be the same equation that I pick. The equation that I want is going to be delta x is VOT plus 1/2 AT squared. But then I want to specialize that to x and then to y. So for the x direction, let's move up here so I have some space. For the x direction, I'm going to have delta x is 45.72. I'm going to drop the units here just to save some space. And then I have VO times t. VO, that's VOX now. So that's going to be VO cosine 30. You can plug in cosine 30 if you want to. And then times t is also an unknown. Plus, this whole thing is going to go to 0 because the acceleration is 0 in the x direction. So this equation has 2 variables in it. So I'm not done yet because I have 1 equation with 2 variables. But I have more to come. Now let me apply it to y direction. In y direction, I'm going to have delta y, which is 0. I'm using the same equation that I used before, equals VOT. So that's going to be VO sine of 30 times t plus 1/2 AT squared. So plus 1/2 times negative 9.8 times t squared. Okay, now I have 2 equations with 2 unknowns. So now I feel a little bit better. This should be a solvable system of equations because I have 2 equations and 2 variables. So let's try to do it. I'm going to work through this one. This is going to be a little bit of a pain to work through, but I want to kind of show it to you because this style of problem does come up quite a bit. So you might have to solve some other problems that are similar to this one. So first, take your favorite equation and start solving. My goal is to find the initial velocity. So I would rather solve one of the equations for t and substitute in so that I can just get initial velocity right away. So let's start with the x equation, and I want to solve the x equation for t. So that's going to give t equals 45.72 over VO cosine 30. And if you like, I can crunch those numbers. So 45.72 divided by cosine of 30 is 52.5. 0.79 divided by VO, okay, equals T. All right, so that came from the X equation. So now let's plug that into the Y equation. Well, actually, I want to do something first to the Y equation. Let me just copy it. So I have 0. Well, let me actually kill 2 birds with 1 stone here and simplify while I copy. I'm going to move the T squared term to the other side of the equation. 1/2 of 9.8 is 4.9. So I'm going to have minus 4.9. Again, that's half of 9.8. T squared, actually this becomes positive because I want to move it to the other side of the equation, equals VO sine of 30 times T. All right, you still with me? All I did was take this equation here and manipulate it a little bit to get that equation down there. All I did was move the second term to the other side of the equation. Let me just clean this up. Okay. Now, what I wanted to do is, you see how one side is T squared and the other side is T? So let's divide both sides by T and get rid of that. So then it becomes 4.9 T equals VO sine of 30. And now let me substitute in the expression I got for T up here. So it'll be 4.9 times 52.79 divided by VO equals VO sine of 30. Okay. Make some space over here. I am out of room. All right. So multiply both sides of the equation by VO, divide both sides of the equation by sine 30, and you get VO squared equals 4.9 times 52.79 divided by sine of 30. Okay, now I can crunch the numbers. 4.9 times 52.79 divided by sine of 30. And this gives me 517.3. That would be units of meter square per second square if you're keeping track. Now take square root of that because this is actually VO square. Take square root of that, and clearly I want it to be a positive result because speed has to be positive, and I get 22.75 meters per second. And there's my answer. Okay, so this was a little bit of a mathematical pain in the neck, which does sometimes happen in these two-dimensional kinematic equation problems. But the important thing is, you'll notice that I just conscientiously followed the basic two-dimensional kinematic equation procedure, just with the gravitational acceleration plugged in as the acceleration. So if in doubt, if you start to get overwhelmed, go back to that basic procedure and just make sure you're following the steps of the procedure. You know, if you faithfully follow that procedure, it will lead you in the right direction.